Hello and welcome to the first in a series of 3 winterization webinars brought to you by Edmonton Valve Fitting, suppliers of crucial fluid systems throughout northern and central Alberta. I'm your host, Fiona Hughes, and I look forward to spending the next 40 minutes with you as we walk through a best practices presentation on winterization and answer some of your questions. I'd like to introduce you to our presenter, an expert on the subject of winterization, Tristian McCallion. Tristian is a local field service advisor at Swagelok Energy Advisors, based out of Edmonton Valve Fitting. Following Tristian's best practices presentation, he'll be answering your questions, so do please jot them down in the chat window and we'll respond to them at the end of this session. Also, we'd love to hear back from you as to what you would like to see addressed in future webinar topics, so do please write in with those thoughts too. Everyone is aware of the need to winterize, but how often do we find ourselves in reactive rather than proactive mode? Usually when the cold weather is upon us. So while the weather is still fine, this webinar series is aimed to put you in good shape and help you avoid production headaches and unnecessary downtime due to cold weather. In today's session, Tristian McCallion will talk about steam tracing. Then next Thursday, the 20th of September, our webinar will be on steam trap stations. Then our final session covering winterization best practices is on Thursday, September 27th, and we'll take a look at unit heaters. So now, over to Tristian to take it away for this week's topic on steam tracing. Tristian?
So what we're going to look at with the webinar today, we're going to talk a little about the purpose of tracing, the types of tracing systems, some of the design considerations, and then we're really going to focus a little bit more on installation best practices, some of the startup procedures, and then we'll open it up to questions at the end. And as Fiona mentioned, probably about 25-30 minutes or so to go through what we've got here. Some of the things that you can actually find as well as you get into some of the really low temperatures, you move up into the Yukon, the Northwest Territories, Alaska, places like that, we might even see tracing put in on steel girders and steel beams to help prevent structural failures due to the really low temperatures that you can see up in that part of the world. Some of the different designs that you can get in a tracing system, well, the first one that we'll look at is the gut line. We don't see this a whole lot anymore. Basically what you're looking at on the slide here is a cross-section of the process pipe. That's the large outer pipe. The coppery fluid in the next inner ring, that'll be our process fluid. And then the tracer actually runs down the center of that pipe. That's why it's called the gut tracer, runs down the gut line in there. It's a very, very efficient way to run tracing. All the exterior surface of that tracing tube is exposed to the process fluid. So obviously we're getting a lot of heat transfer there. We're not relying on a single point contact. We do see it once in a while. It's not that common anymore. And the reason that it's not that common anymore is because it's very difficult to install and to maintain. You can imagine we have to set this up as we're setting our piping up. We have to find some way to support that gut tracer inside the system. That's not always the easiest to do without restricting flow or creating potential problems. Maintenance obviously is going to be an issue. The only way that we can maintain that line is by getting into the pipe, which means we have to shut the system down in order to get in there. If there's any leaks or any other problems with it, we may not know about it until it's too late. So this type of tracing is very, very limited in application these days. The only time that we ever really see it would be for sulfur. That's probably the most common one that we run into, or something where the temperature is very, very critical. So fairly minimal usage, but it is still out there once in a while. The next type that we see, again, not the most common one out there, but something that does pop up, is the jacketed design. And we see this on pipe, and we also see it on vessels, especially if we're using it to heat up a small tank of something. We see that in the food and pharmaceutical industry a fair bit, where we have jacketed tanks or jacketed piping. And if you look at the picture here, on the top left-hand side as we're running in, that's our steam supply coming in on the top, and it drops down into, it's basically a coaxial pipe or a pipe within a pipe, so similar to a gut design, but instead of the gut design where the tracer's on the inside of the process line, in this case the tracer's on the outside and surrounds that entire piping system. There are a number of benefits to this. One, again, we do have high energy addition, so most of that energy is being directed into that pipe, so we have a large surface area for the heat transfer to take place, so it does improve the efficiency. We do have to make sure that it is insulated properly because we're obviously going to have some radiant loss coming off the outside of that pipe. So it's not as efficient as a gut system, but it's still one of the more efficient systems that are out there. Disadvantages with a system like that is it can be very expensive to set up and install. This is probably the most common design that we see out there at the moment. It's just a bare tube tracer. And the majority of facilities that we run into now where you are running some type of tracing, be it glycol, be it steam, this is the sort of design that you're going to see. It has a number of advantages over the previous two systems where it's very easy to install. The maintenance on it and the ability to make changes to the system, it's very conducive to doing that. And it is a very reliable system. We generally have minimal connections because we're running endless tubes, so there are fewer connections to deal with and have potential leak points in it. The negative with the system, though, is there is relatively low heat transfer, especially when we look at the surface area. Heat's going to be transferred primarily through the contact points. So if we do have any space between the tubing, we're not going to have a direct contact point to allow that heat to transfer. So if there is air gaps and things, the efficiency significantly drops. We're going to wrap that pipe and tracer in insulation, so some of that heat is captured and radiated back into the line, so we do see some energy efficiencies and savings there. But as far as comparative to the gut design and the jacketed design, it's certainly nowhere near as efficient. Having said that, though, there are some things that we can do to improve the efficiency of the system. One of them is to use a heat transfer material or heat transfer cement, and we'll talk about those in a little bit as we get into this a little bit further. So those are the three main types of tracing that are out there. When we're selecting the tracing that we want to do and how we're actually going to trace and which fluids we're going to use, there's a few things that we really want to look at as we're making our decision how we're setting the system. So some of the things that we're going to need to consider is one is going to be the startup time. Obviously, as we're starting a system up from a fairly cool state to the warm state, we're going to need more energy to create that increase in temperature. Once the system's up and running and we're just maintaining it, it's certainly not as much effort or energy required to keep the system in that. So if we have a system that we're bringing down and starting up a couple times a day, we may need something that's going to allow us to bring the system up fairly quickly. Conversely, if it's something where we're just putting it in for freeze protection, we know that we're going to be running it through the entire winter. We can start now and bring systems up and give them a day or so to come up to operating temperature and have no issues with it. We're not going to need as many tracing lines or something that's going to heat up as quickly as we would with something that has to start up once or twice a day or even more than that. We also want to look at the fluid that's going through the main lines, the process lines. What are our temperatures that we're going to be dealing with there? Are we just looking for freeze protection? Are we looking to keep that process temperature at a specific temperature? And if so, what is that range? And if we're dealing with that, then that's going to determine the type of fluids that we're dealing with or the type of tracing that we're going to deal with. If we're dealing with lower temperatures and maybe just freeze protection, well, we can use electricity, we can use steam, we can use glycol, we can use any of those to keep that freeze protection in place. As we get into higher and higher temperatures, our choices become more and more limited. You know, as soon as you get in some of the higher ones, maybe you are restricted to glycol or steam, and as you get into the extremely high temperatures, glycol may even boil off. So at that point, we're going to want to be looking at a steam system to provide it. If we are looking at a steam system, we want to know what sort of what pressures we have available to us. As a general rule, the lower the pressure, the more efficient our energy transfer is going to be. So if I can get away with just freeze protection, I'm going to be looking at a 15, 30, 50-pound system to maximize the efficiency. I can pull it off flash steam. I can use it find the source from anywhere in my steam system. If I need to get into those higher temperatures, then I may have to go to a higher steam pressure. Okay. If I am running steam as well, I want to consider my condensate recovery. I don't want that condensate dumping to the ground. In today's world, our thermal cycle, the efficiency in the thermal cycle is such that we have to be operating at such an efficient level, we can't afford to dump that condensate to the ground. That condensate contains a lot of the energy that was put into it to bring it up to operating temperature. When it goes through the tracing line, it's just giving up its latent energy, ditching that off. We want to bring the sensible energy back to the boiler house as hot as possible, so we absolutely have to be recovering. If we are running a steam system, we want to make sure that we have that in place. We also want to look at how long the process line is. That's going to help determine the number of tracers we need on the system. Are we going to run a single tracer? Are we going to run multiple tracers? And then we're also going to want to look at the material selection that's on the system as well. Anytime we're dealing with pressures over 15 psi, we are under the ASME code. There's maybe 1 or 2 states out there that don't deal with ASME, but 99% of what we're dealing with around North America is going to require us to be under the B31.1, B31.3 code. And all of that tells us we have to have specific materials, and the designs have to be of a standard that allow us to operate safely. We don't want to be using garden hose as the tracer. I mean, you can laugh about it, but I have actually seen it out there where people are running rubber hose and things that is not rated for the steam pressures. You know, you think, well, I'm only running 20 psi or 30 psi. There's an awful lot of energy stored in that steam at that pressure, or that condensate at that pressure. So we have to make sure that we are using the correct materials and have correct designs in place. One of the other components that we really want to specify on is the valves. When we look at valves, we want to specify, at a minimum, a Class 4 shutoff valve. Valves will have a 6-class shutoff system. Class 1 is basically an agreement between the manufacturer and the supplier that I'm going to give you something. It's going to have some end connections on it. It's going to have a handle on it, and it may or may not restrict flow to some level. Those are the valves that you pick up in the discount stores for $2 or $3 for a 1-inch valve. You know, I mean, you're getting what you pay for. A Class 4 shutoff valve will allow you 0.05% of that rated valve capacity. You can come across that valve seat, and that valve is still considered leak tight. So even with a Class 4 shutoff valve, it's still leaking across the seat. But it's a very, very minimal amount, and it's something that we can work downstream of and feel safe about it. One of the things that's really nice with the tracing systems is because we're generally dealing with lower pressures or lower temperatures, we can often get away with a Class 6 valve. And the main difference between a Class 4 valve and a Class 6 valve is Class 4 is about as good of a shutoff as you're going to get with an all-metal seated valve or all-metal components in that valve. A Class 6 valve, you're generally going to see some kind of elastomer in there, be it PEEK, be it Teflon, which will give you reasonably good temperature rating. You can probably get away with up to about 100-pound steam or so with most Teflons and most soft-seated valves, which for tracing applications works out great. Teflon's going to top out at around that 400-degree F mark or 200-degree C mark, somewhere in that range. So with the valves, we can actually get into a higher classification of shutoff and provide something that does dramatically improve the performance. Class 4 valve, 0.05% of rated valve capacity. When you get into a Class 6 valve, you're looking at milliliters per minute versus port diameter. So basically a bubble-tight shutoff is what you're getting with a Class 6 valve. You're going to pay more for a Class 6 valve than a Class 4 valve? Well, yeah, I'm afraid you are. But it's something that you can work downstream of, feel safe with, and continue from there. We want to make sure that we've got a standard for the fittings. We want to make sure we've got a standard for the tubing size and material. We don't want to be keeping 10 or 15 different configurations in stores. It increases our cost. Anytime we can standardize and reduce the number of components that we're looking at, it's certainly going to make life a lot easier for the warehouse people and bring the overall cost of owning that tracing system down. We want to make sure we've got enough insulation on there, and there are a number of really good tools out there that will allow you to determine how much insulation you need and what the payback is. You know, you can get in, dump in the information on the size of pipe that you're using, the type of insulation you're using, the type of lagging you have over the top, the ambient conditions that you're dealing with, and all these things will spit out and tell you how much heat you have to replace, what your general BTU loss is, and how much insulation is, or what the optimum amount of insulation is to put on your system. Relatively speaking, insulation is very inexpensive when compared to the energy loss, so it's one of those things where more is generally a better option than less. Gauges is something we really like to see in our system as well. It's a fantastic diagnostic tool. They're relatively inexpensive, again, from the startup position. If you have a header, a tracing supply header, and then the condensate return header, if you put a couple of gauges in those locations, you can tell an awful lot what's going on in the system without having to break into lines. For the $50, $60, $70, whatever the gauge costs you, it's a very, very cheap maintenance tool and very easy to put in when you're starting your system up or designing your system. After the fact, it obviously gets to be a little bit more complicated and a little bit more work, but if you are setting your system up the first time, I would highly recommend including gauges. As many as you can get in the system, it's an excellent diagnostic tool. And then the last thing we're going to look at is when we're running it are the steam traps. It's kind of the end point, especially if we're running a steam system, obviously. That's the end point of the steam line as we're coming off the tracing. So we want to make sure, again, we've got standards for the steam traps and keep the supply folks happy by minimizing the amount of inventory we have to keep in stores. Okay. So what we're looking at here is a typical tracing line. So when we're coming in, we're going to come off the steam line right at the top here. We always come off the top of our steam header, and the reason that we come off at the top of the steam header is it allows for a clean, dry vapor to come off. If I'm coming off the bottom of the steam line down here, then if there is any condensate or corrosion material accumulation that's in the line, then that can drop into my condensate line and create some potential, or excuse me, my tracing line, and cause some potential for fouling or plug-ups or potential for water hammer. By coming off the top of that line, we're going to dramatically improve the quality of the steam that we're running in our tracing system. We also want to make sure that whether we're running steam or glycol as our primary tracing fluid, that we're coming off a dedicated line. We don't want to be coming off the steam supply line that's going to, say, an air handler or a piece of process equipment. Because if I have to shut that piece of process equipment down, then what can happen is if I shut that line down, then obviously my tracing is going to get shut down as well. So I want that steam line to be one of the main steam lines that I'm using, so it can't be shut down, so I don't have to worry about losing my tracing if one piece of equipment comes down. After I come off that steam line, I'm going to jump into, called a jumper, going between the steam line and the point at which the tracer is attached to the pipe. At that point, I want to try and keep that as short as possible. Sometimes it does have to be a bit longer in order to get out to where it's going, but keep it as short as possible. And I want to make sure that it's insulated as well. After I get into that, I'm going to connect my tracer to the actual process piping. I'm going to band it on there. I'm going to put insulation and wrap it around the tracer and the traced pipe. I'm going to run along. The maximum length that I want to make my trace line is about 100 feet. As soon as we start getting longer than that, then we're going to need to be looking at special engineering. We're going to have to figure out what the flows are. We're going to have to size the steam traps a little differently. But if we keep things under 100 feet, as a general rule of thumb, that's going to allow us to be very generic with our selection of components and keep things very, very simple going forward. After we come off of that trace line, we're going to drop down, and we're going to go into the condensate return header. So when I go into that condensate return header, I want to come into the top of that condensate return header. It'll help reduce water hammer. And also on that, the jumper line coming off the tracer, I want to keep that as short as possible. And I also want to make sure that that stays insulated as well. If we're looking at the number of tracers, there's going to be a couple of different positions that we want to run those tracers in. Generally, they want to be installed at the bottom of the piping. The reason that we put it at the bottom of the piping is basic engineering, that heat's going to rise. So we want to make sure that the heat's allowed to rise up. If I put those tracers near the top of the pipe, then obviously I'm not heating as efficiently as I possibly could. When I'm installing the tracing line as well, a couple things we want to avoid. If you look at the very top picture there where I've spiraled the tracer around, that's not something we usually want to see. That could create potential low spots in my condensate line and pool up condensate, which can result in water hammer. Same thing on the middle picture where I've got the low spots inside there. It can cause condensate to pool up in the low points, again, potential for water hammer. The other thing that can happen there, if I'm not snug against that piping, then I can run into issues with air acting as an insulator. 1/1000th of an inch of air is the equivalent to 13 inches of copper as an insulator. Air is a very efficient insulator. So if I have a thin space between my tracer and my pipe, it's certainly not going to be anywhere near as efficient as it could be as if I do it on the bottom one, where I properly support that tracer against the pipe and make sure it's tight and snug up against there. Things that we can do to improve the efficiency of the bare tracer, and I mentioned this as we were talking about bare tube tracing right near the start, is to use a heat transfer cement or some preformed insulation that will help transfer the heat efficiently from that tracer into the pipe. So if you look at the picture we've got here, on the top you can see you should be able to see this, the tracing line. That's the heat transfer cement, and then that's the aluminum channel that helps support it. So if I look at a cross-section of my pipe, the large pipe is the process pipe. The line, the tube with the squiggle line in the middle is my tracer. The gray area here is my heat transfer cement, and that can either come preformed or as a trowel-in material. So it's almost like a tar kind of material. It can be kind of messy, so most people will go with the preformed. Licorice is a common term for it. feels kind of like recycled rubber when you're looking at it. And then there's an aluminum channel that goes over top of that. And what happens is as you put that on, snap it in place, and then bend that all down to the pipe, then when you start your system up, as the steam or the glycol starts to heat that tracing line up, it causes that heat transfer cement to liquefy and flow all around that tracer and connect to the pipe. And then as it heats up a little bit more, it actually turns into a very hard cement. It's almost a stone kind of feeling material. And that will allow the tracer to direct its energy much more efficiently into the pipe. It's calculated out that one of these tracers with the heat transfer cement on it is the equivalent to 3 or 4 bare tracers, so it is a lot more efficient from that standpoint. And that pops up is if we are dealing with small tracing lines or small process lines, we can actually get pre-engineered solutions for us. There's a number of different companies out there that can do this, and there's a number of different designs. The nice thing with something like this, if I'm dealing with a process line that's 1/2 inch, 3/4 inch, even up to 1 inch, we can get into some of these solutions for us. And the companies that manufacture them, they do an extremely good job with the engineering side of it. So you basically give them your parameters, what temperatures you need to maintain, what your operating conditions are, what your ambient conditions are, and they will come back with a solution for you, and you can get endless rolls of this and, you know, several hundred feet long that will allow you to put this stuff out very simply, very efficiently. It costs you a little bit more for the material side of things, but by the time you figure the installation costs, your savings are fairly significant. You can see by the picture up there, there's a couple that they've got. They've got a light steam and a heavy steam. It doesn't have to be steam. I can run glycol. They'll do an electrical solution as well for us, so where you can run electrical tape along it. You notice they've got a light steam and a heavy steam on this one, the main difference being on the light steam, if you look between the tubes, there's actually some space. On a heavy steam, it's just referring to the fact that the tubes are in contact, so we've maximized our heat transfer through that system. When we look at tracer efficiency, some of the things that we really want to focus on as well is avoiding situations like this. And I know there's a few people out there chuckling how to get a picture of my plant. You know, pictures like this are something that come out. If anybody walks around the facility, if you have a large number of traps out there, everybody's going to be familiar with a picture like this. One of the things that we really try and emphasize when we come in and do our training and when we do our steam system engineering is don't componentize the system. You know, you look at a picture like this and the first thought is, oh, my steam traps are failing or my valves are failing. And realistically, it can be a result of the whole system. We want to look at the system as a whole. We have to understand how the components work within the system, but we certainly want to make sure that we understand the system as a whole. You know, one of the best ways to maximize the efficiency as well in the system is to try and capture some of the steam that would generally be wasted. So if there is a chance to catch some flash steam from a higher pressure application and bring it in through a flash tank and drop my pressure down to 20, 30, 50 PSI or 5 PSI, one of the lower pressures, and use that flash steam, I really maximize the efficiency of my system. I mentioned the thermal cycle kind of when we started out here, and anything that we can do to pull the BTUs out of the system and prevent them from being vented to the atmosphere is going to dramatically increase the efficiency that we deal with in our system. So anything we can do, like capturing flash steam and using it for the tracers, big savings that are available there. One of the other things that we notice as well when we're dealing with tracers is people tend to start them up. If there's any problems, we'll kind of fix them, then they get forgotten about until the system gets shut down and then started up again the next year. We want to be maintaining our systems on a regular basis. Tracers don't use a whole lot of energy individually, but when we add them up and look at the total number of tracers that are out there, the amount of energy they consume on a plant-wide basis is actually very significant. So to walk by and see one tracer leaking, or maybe you notice a few tracers leaking, or you see a tree like this where we've obviously got some fairly significant issues, the payback on fixing something like that is extremely short. You know, we're probably talking 2 to 3 months payback before we start receiving the benefits of being more energy efficient. So anytime that we can fix it, we want to be maintaining these things on a regular basis. We want to be testing those traps on a regular basis and continuing on from there. When we start the system up, we want to make sure we're doing a few things as well. First off, do we have a written procedure? We don't want to just go out there, start opening valves, okay, it's on, walk away, wait until we see our first cold day and then run into some problems. You know, does the standard operating procedure or written procedure, do we have a form for that? Does the plant have one already set up? If not, we should probably look at getting one. Some of the things you want to consider when you're looking at your standing operating procedure is make sure you lay out how many people that you're going to need. That's going to vary. If you're in a situation where your supply header and your return header are in close proximity to each other and everything's laid out nice and clear and labeled properly, well, maybe you can get away with one person opening the supply, opening the return valve, blowing the strainers down on the steam traps if you're running steam, and being able to do everything by themselves. If your supply line and tracer or return line are a long distance apart, 100 or some feet apart, or even more than that in some cases if we don't have the system laid out properly, well, then in that case, we're going to want multiple people, and we're going to want to make sure they've got a way to communicate efficiently. So do they have radios? We want to think about the safety equipment that's going to be required as well. Obviously hard hat, safety glasses, steel-toed boots, long sleeves are all pretty good common sense things, but are we going to need anything else? Is there areas that we're going into where we maybe need gas monitors or things along those lines? Okay. We definitely want to do a pre-startup meeting so everybody's aware of what we're doing. And you're going to walk through the system as well. So before you even start opening one valve, you want to walk through that system. Okay. Generally then, after you've done the walkthrough, you're going to identify the lines that you're going to open up and the components that are on that line. Where's the supply valve? Where's the return valve? Is there a steam trap on it? Is there a strainer on that steam trap? Where's the actual tracing line running? Okay. Once we've done that, general rule of thumb, especially with the steam ones, is we're going to open the blowdown valve on the steam trap station to allow condensate, non-condensables, and contamination to be removed from the system. After we've got that, we're going to open up our supply valve, leaving that blowdown valve open or the strainer valve open. Once we start to see evidence of the condensate and the non-condensables and the contamination that's being removed from the system, we're going to close that blowdown valve and then start checking for proper operation of a steam trap or checking for temperature, either using a temperature gun or infrared or whatever we're using to check our system up. So, well, that's basically tracing in a nutshell from the start to the finish, starting the system up. I will open the floor up to any questions. Okay, I see one's popped up here. What type of tracing is the most efficient, electrical, thermal fluid, or steam? That's going to depend a little bit on a number of different factors. Obviously, if you have steam readily available in a plant, steam tends to be one of the more efficient systems to use. If you don't have steam in your plant, then obviously it's going to be a lot more expensive because now you're looking at installing a boiler, one of those other ones, in which case electrical or glycol or a Dowtherm or some other thermal fluid are going to give you a better choice. So again, depends a little bit on what you have available to you. Electrical is generally a fairly inexpensive one to use if you're using shorter runs or it's not a real common thing to do, but it does have some limitations for intrinsic safety in certain areas of the facility. It's not always the most efficient system to run in there, and it can be somewhat expensive to install. You sometimes have to get special equipment and things to install in there. Length of tracers, somebody's asking why 100 feet for the length of tracer. Generally, that's going to refer to a steam system. When we're looking at 100 feet as a maximum length on the tracer, then we are going to be, with that 100 feet, we can guarantee that we're not going to go change phase from the vapor to the liquid too early in the process where we're just running condensate down the bulk of that tracing line. When we're doing tracing with steam, we want the latent energy, the phase change energy of that steam to be given up in the tracer. That's what does the most of the heating. So if I give my latent energy up and then I've got another 100 feet where it's just condensate going through the line, the condensate's really not doing a whole lot of heating in my system. It's certainly nowhere near as efficient as the steam is. So that's why we want to kind of limit as a general rule of thumb to about 100 feet. I got one here. Got one about steam traps, types of steam traps we're going to be considering. That's a good lead-in for next week because we are going to be talking about steam traps and steam trap stations. So if that's okay, I'll leave it to next week. And another one here on, does the cement have any effect on tracer life, longer or shorter? Not that I've seen. The big issue with the cement is if you are doing maintenance, it's literally cemented onto the pipe. So at that point, the maintenance becomes very difficult for that tracing line. So you want to make sure you're dealing with good components in there. Anytime you're coming around the flange, you're going to want to come off. You don't want to cement that tracer to the flanges. You want to come off there with a jumper and put in a union on your tubing at that point, just to allow you to do maintenance. But yeah, I haven't heard anybody saying anything negative about the life of it. I guess you might run into some issues with corrosion, potentially with some dissimilar metals if you're using stainless steel on carbon steel, and there's going to be some expansion, contraction stuff, but for the most part, I've seen stuff that's been cemented on pipes for 20, 25 years, and the cement's going to break down before the tubing and the piping will generally break down. Another one's popped up here. Is there a benefit to tracing with copper or stainless steel or vice versa? Most of the applications that we see these days are going with stainless steel. A couple of reasons for that. Copper does have an advantage that it does transfer heat a little bit more efficiently, but the downside to the copper is most plants don't run copper in the plant, so you've got an extra material that you have to carry, whereas if they're running stainless steel, the parts are probably going to be in stores, they're going to be readily available, so if you do have to do any maintenance in the system, you can. And I've also seen some corrosion issues pop up with the copper where you can build up some corrosion material accumulations, which can foul up your strainers and cause potential problem for your boilers as well if you're not treating the steam properly.
So it's time to wrap up this session. Tristian and I would like to thank you for your time and the great questions posed today. I hope you've been inspired to begin your winterization action plan and that you'll join us next Thursday, September 20th, for our session on steam trap stations for tracing. To review or share today's information with colleagues, you'll be receiving an email from us with the webinar replay link. And as a special thank you for your participation today, we'll be including a guide for best practices for steam tracing. On behalf of everyone at Edmonton Valve and Fitting, we'd like to thank you for participating in today's session, and we look forward to joining you all next week for the winterization theme topic of steam trap stations. Goodbye.